So far, when we've needed to calculate a derivative, we've used the definition, and it's actually been working okay. You know, it takes some algebra, but we can do it. So for a function like this, the derivative is just going to be the limit as h goes to 0. We have to write down f of x plus h here. So that's going to be 1/2 x plus h squared plus x plus h minus 1 minus, and then we have to write down f of x right here. So that's 1/2 x squared plus x minus 1 all over h. And then we have to do a bunch of algebra, right, to make it so that we can evaluate this limit. And it's kind of annoying to have to do this algebra over and over again. We've done several examples similar to this one, but it's doable, right? It's doable. But this function isn't that complicated in the grand scheme of things. In lots of applications, very complicated formulas show up. Something like, say, this. Imagine trying to find the derivative of this function using the limit definition of a derivative. So what we would need to evaluate is the limit as h goes to 0 of x plus h squared times sine of x plus h over x plus h plus 2 over the square root of x plus h minus 3. Okay, well that's just plugging in x plus h. Now we have to subtract x squared sine of x over x plus 2 over square root x minus 3 all over h. And I mean, I don't know about you, but I think this is crazy. It's possible that maybe this limit is something we could evaluate, but it would take us all day. It would take a lot of hard thinking about how sine works. This just looks like a complete mess. So if this is even possible, it's definitely not practical. But on the other hand, this formula, it's actually built out of just a few simple small pieces, right? There is an exponent, there is a quotient, there is addition, there is a sine function, there is a square root function, and there is a multiplication function. Right? And that's about it. Oh, I guess there's subtraction too. So if we knew what the derivative of each one of these kind of scenarios was, if we had some sort of shortcut or, I don't know, some kind of rule to tell us what the derivative of each of these scenarios is, then maybe we could assemble all of these pieces into a derivative for the entire function. So that's what we'll try to do. Rather than wrestling with these big impossible limits, we're going to come up with derivative formulas for these very simple scenarios, and then figure out how to put them together into more complicated functions. So what we're after is a derivative rule for every possible situation, every possible way of putting two pieces together into a more complicated formula. And if we can come up with a derivative rule for every single way of combining pieces, then we'll be able to differentiate any formula just by breaking it up into its constituent pieces and applying all of the appropriate rules. Of course, to find all of those derivative rules, we are going to have to use the limit definition. And that might be tricky in some cases, but we'll do our best. To get some experience with coming up with these rules, let's start with maybe the simplest cases. Here's one simple case. So let's find the derivative of a constant function. Right? So if f of x is just a constant c, what is the derivative? Well, until we have some derivative rules that we've figured out, the only way we can find a derivative is by using the limit definition. So let's write out the limit definition. We need f of x plus h right here. But since f is the constant function, f of x plus h is just c minus f of x. But again, f of x is the constant function, and so it just produces c. over h. So this is the limit as h goes to 0 of 0 over h. That's 0. So now we know that the derivative of a constant is 0. Right? If we wrote it in Leibniz-style notation, it would look like this. That kind of makes sense because if a derivative is a rate of change, constants don't change, and so their rate of change ought to be 0, and sure enough, it is 0. So anytime we take a derivative of just a constant, we get 0. Let's look for other simple cases where we can get derivative rules. How about if we have a function that has a derivative and it's multiplied by a constant? So what is the derivative of a constant times the function? I'll use Leibniz notation this time. So we're looking for the derivative of c times f of x. All right, well, we don't have a derivative rule for this situation yet, so we have to use the limit definition. This is the limit as h goes to 0 of c times f of x plus h, right? We're plugging x plus h in to the function, minus c times f of x over h. But look, in the numerator, both terms have a c, so we could write this like limit as h goes to 0 of c times f of x plus h minus f of x over h. But this constant, right, that's a constant multiple. This c is not a function of h. And so the constant multiple rule for limits says that we can just move that c outside of the limit. So now we have c times the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, so this is c times, what is this limit? Well, we don't have a formula for what this limit is, but we do have a name for what this limit is. This is just the derivative of f at x. Or I guess I said I was using Leibniz notation, so df dx. All right. So what we found is if we ever need to take the derivative of a constant times a function, it's just the constant times the derivative of the function. This is probably what you would guess, right? Essentially what this derivative rule is telling us is that if we have a constant multiple, we can just move it outside of the derivative, which is probably what you would have guessed anyway. All right, well, these first two examples are pretty straightforward. Let's see if we can come up with a derivative rule for a more interesting function. How about a derivative rule for the x to the n function? In particular, let's come up with a derivative rule for the derivative of x to the n if n is a positive integer. So if n is a negative integer or not an integer at all, the argument that we're about to come up with won't work. Okay, so to find the derivative, we need to, right, until we have a derivative rule, we have to use the limit definition. So limit as h goes to 0 of f of x plus h minus f of x over h. So this is the limit as h goes to 0 of x plus h to the n minus x to the n over h. Okay, now we know that n is a positive integer, so this exponentiation represents repeated multiplication. And since it's positive, n has to be at least 1. So let's think about what happens if we repeatedly multiply x plus h times itself, right? So this is really x plus h times x plus h times x plus h over and over again. So think about what happens when you multiply something like this out. What you get is a big sum of terms, and each term is you form each term by choosing one thing from each factor. So one term that you get out of this product is x times x times x times x with all of the x's, but there are n factors here, right? N copies of this. So if you form the term that is just all of the x's, you get x multiplied by itself n times, so that's x to the n. Okay. what about all of the terms that you can get by choosing only one h? Well, there's x times x times x times x all the way up to the last one, but then in the last one you choose h. So that's one way to get x to the n minus 1 times h. But there are other ways to get x to the n minus 1 times h. So we could choose an h in the first term and then all of the x's. Or we could choose an x and then an h and then x's in the rest of them. So how many different ways are there to choose only one h? Well, there are n ways to choose only one h because we have n different factors that we could choose the h from. So there's n ways, n different terms. When we multiply this out, there are n different terms that look like x to the n minus 1 times h. All right, and the rest of the terms all have h squared. So everything else is h squared times some stuff. Turns out we aren't going to need to know what all this stuff is. All right, so that's this first piece here. Minus x to the n over h. And now, let's see, this x to the n cancels that x to the n. And now everything in the numerator has a factor of h. So we can cancel a factor of h. And we're left with the limit as h goes to 0 of, oops, I made a mistake here. This isn't an h. This right here is an n. This is the h. Okay. So n times x to the n minus 1 plus h times whatever that stuff is. But this stuff is polynomial, and we're taking a limit as h goes to 0. So this h right here is going to 0, and the stuff in the parentheses it doesn't matter what it is because h is going to 0. So we get n times x to the n minus 1. All right, so we just found the derivative of x to the n. It's n times x to the n minus 1. If we want to write this in Leibniz notation, we could write d dx of x to the n is n times x to the n minus 1. So we're going to call this the power rule for derivatives. And we've only proved it for positive integers. But in fact, this power rule is true for any exponent. So as long as this exponent is a constant, then the power rule is true. It doesn't matter what constant it is, it can be any real number. We've only proved it for positive integers. We will prove it for all real powers later in the quarter. But for now, I guess I'll just ask you to take my word for it. All right, so we have these three derivative rules. Let's see how we can use them. Let's look at some examples of using them to calculate derivatives. So let's start out by finding the derivative of this function. So we're going to find the derivative of 4x cubed. Well, there's a product here, right? This is 4 times x cubed. And the constant multiple rule says that we can take this 4 and move it outside the derivative. So 4 times the derivative of x cubed. All right. Now, since this ddx symbol is still here, that means we still have a derivative to calculate. So we can't stop yet. We aren't done. Fortunately, the derivative of x cubed, we have a derivative rule for that. We can use the power rule. Right, the power rule says that you take the exponent, it comes down, and then the exponent decreases by 1. So 3 minus 1 is 2. So this is 12x squared. All right, so we were able to calculate this derivative just using these derivative rules and without having to calculate any limits. You can see if we have enough derivative rules for whatever formula we're faced with, we can save ourselves a lot of time by using these derivative rules rather than having to calculate big complicated limits all the time. All right, let's look at another example. let's find the derivative of the square root of x. Well, do we have a derivative rule for square roots? Well, we didn't state it that way, but remember the power rule works for any exponent, which we haven't proved yet, but we will eventually. So if we can rewrite a square root as a power, then we're good. And we can rewrite the square root as a power. It's the power of 1/2. So the power rule says that the old power comes down in front as a multiple, and then we subtract 1 from the exponent. So this is 1/2 times x to the minus 1/2. Now if we want to, we can rewrite this to make it not have a negative exponent, I guess. So 1/2 times 1 over x to the 1/2, but that's the square root of x. So this is 1 over 2 square root x. We don't 100% need to rewrite it this way, right? 1/2 times x to the minus 1/2 is okay, but I don't know. It seems like the right thing to do. All right, so let's look at one more example. How about the derivative of 1 over x squared? So derivative of 1 over x squared. Well, you might think, hey, there's a quotient here. Can't we just move this outside? Well, do we have a derivative rule that says we can do that? No, we don't, right? This is built out of a quotient, and we don't have a derivative rule for quotients, so we can't do it that way. We have a power rule. Could we rewrite this function as a power of x? Yes, actually, we can. Right? 1 over x squared is the same thing as x to the minus 2nd power. And now we can use the power rule. So the power comes down, minus 2 times x to the, and then we take our old power and subtract 1 from it, so minus 3. So this is minus 2 over x cubed. All right, so you can see that if we can just get enough derivative rules, we'll never have to take limits to calculate derivatives basically ever again.